Okay, and we will go through some mini review for the homework as well. I do encourage you to attend on time, so in live format, so this way you will not miss anything. Sometimes when I hit record, I may miss something, okay? The other thing is when you synchronize, you can ask live questions, so we have more interactions going on, okay? Now I have a list. I've been recording how many questions I've asked and what's your responses. I'm gonna keep doing that, so kind of like an interaction process, okay? We'll probably have more going down in the road as well, okay? So let me share the screen of the lectures, all right? So this is actually the first homework. You're gonna see something similar to that. Not exactly identical, but something similar, all right? So it's gonna be problem answers, okay? So we have like 5 or 6 or 7 each type of problem. So you need to solve them, all right? And now for the format of the homework, okay? What we need you to do is to use either engineering paper or a white print sheet or anything that blank. And I want you to guys scan it or take a photo of it and convert it to PDF file up to the assignment tab from the Canvas, okay? Now, I want you to either print this out as a cover sheet or when you're trying to work it out one by one, copy the problem. So throughout this copying process, look at the problem itself, you will not miss the key information from the problem, okay? So that's mandatory, okay? So if you just turn in answers, the grader might have a trouble identifying which problem that is. So we may have some missing points for you, okay? So make sure you have the problem covered, okay, at the first page, okay? So we'll talk about some of the problems, but before that, okay, let's go back to the slides, okay? Let's go back to the slides. And we finished talking about chapter 2, which is design, all right? So I want to kind of do a little bit of review on what we talked about last time, okay? So I have this question. If I have a design strength, okay, and I want to get my nominal strength, all right? Let me say this again. If I have a design strength, okay, and I want to get my nominal strength, okay, and then once I have my loading, I will get my ultimate strength, MU, okay? So on my left-hand side, I have my MN, which is nominal strength, and the right-hand side is the ultimate strength, okay? So which one should be higher, okay? So left-hand side, nominal strength, right-hand side, ultimate strength, MN, MU, which one should be higher? Khalid, you still there?
Yeah, I'm here.
Oh, I'm sorry, you're gonna be my first victim today. So
yeah, it's okay. MN should be greater than MU.
Okay.
Or equal to.
Okay. So you think MN should be bigger than MU or equal to, right?
Yeah.
Okay, that's the correct answer. Okay, that's correct. Good. That's the correct answer. Okay. So the key thing is we have to make sure that the nominal strength is bigger than the ultimate strength. Okay, so that's from the second chapter. Now, once we finish the design process, we'll start looking at materials, okay? So for reinforced concrete, okay? Of course, we'll have the concrete, all right? And we also have the reinforcing steel. So today, we're going to talk about them separately, okay? First of all, concrete. So we know concrete have a wet or dry state, okay? Uncured and hardened state. So right now, we are mainly interested in the hardened state, okay? So for the standard or for the design purpose, these are the parameters that we're interested in. Compressive strength, how much concrete can take in terms of compression. Tensile strength, how much concrete can take in terms of tensile stress or crack. Modulus of elasticity, Young's modulus. Volume change, okay? Volume change. So these are the 4 critical parameters we're going to use to evaluate the concrete. Okay, and to talk about the concrete composes of a paste and aggregates. Okay, so we have the coarse aggregates like pebbles or rocks, or we have the paste and powders mixed with water, and then everything cemented. Okay, so that's the composition of concrete properties. Okay, now for the concrete, the paste is actually a very ancient material. Okay, this dated all the way back to the Portland cement. Okay. And actually, the ancestor of that is pozzolan cement, which is fly ash, silica fume, ground granulated blast furnace slag. These pozzolans particles, you can think of it as more like a volcano ashes nearby the volcanoes, where ancient people used this ash to mix as a cement. And they built a lot of buildings with it. And some of them are still standing today, okay? The Portland cement is more of a modern construction materials, and it's more chemical fabricated. We take some of the slag and dissect them into small particles and functionalize them and to make them Portland cement, okay? And from the cement, and add some water, we have our paste, okay? So from aggregate side, we have two types of aggregates. Coarse, which means gravel or crushed stones, or fine, sand. So we usually get the fine in terms of sand from rivers or some seabed. We don't usually use the seabed sand, okay? Now the difference between the river sand and seabed sand, the river sand is more of sediments. Their tiny particles has been filtered from water washing them. And the seabed sand usually are containing microbial organism or animal skeletals. So typically, if you see sand from ocean bed, they're pretty weak and ductile. So we don't usually use them as construction materials, okay? All right, so we have all these components together, okay? And they're organized together in terms of percentages. So these are general description of the components, right? So the paste takes usually about 25 to 40%, okay? 25 to 40%. And see that's the majority part of the volume. And aggregates take about 60 to 75%. So you can think of it, concrete essentially just aggregates binded by the cement. Hence, we usually call the cement as binders or binding materials, okay? So you can think like glue to glue those particles, big rocks together, okay? So we don't usually use a lot of cement, okay? We don't usually use a lot of cement. Why? Because cement is expensive. It's kind of expensive, okay? So the cement is only 7% to 15%, very small portion of it. And we use quite a bit of water to mix it. So 14% to 20% water here. And we also need some air, and the main purpose of air, bubbles, right? To allow the concrete to flow, better, okay? So that's a rough composition of the concrete materials. And we'll have exam problem, talk about them, okay? We have exam problem, talk about this, okay? All right, so what are the important parameters for the concrete we need to evaluate, okay? So first of all, we need to evaluate in terms of strength, right? That's for hardened concrete, okay? And the quality of the hardened concrete means strength is highly dependent on the amount of water used, okay? So that means the water-cement ratio is very critical. Now, you guys probably have taken the construction materials or going to take construction material courses, and you will learn from there that a higher water-cement ratio means your concrete is more flowable, liquid, but during harden, it's low strength. And the lower water-cement ratio means you have higher strength, but it's very hard to work with, okay? So there strikes a balance of the optimum water-cement ratio, depends on your need, okay? Depends on your need. All right, so we like to reduce water as much as we can to enhance the strength naturally, right? To enhance the strength. But not always the reduction in water, not always bring us benefits. Sometimes it also bring us disadvantage. But before, let's take a look at the advantages, right? What kind of advantages we can have by reducing the water ratio. So first, by reducing the water ratio, we increase compressive and flexural strength, okay? So make it stronger, all right? What it does is, due to a low water-cement ratio, we have a full hydration of the materials and left a very few air bubble afterwards, right? After water evaporates. So we have less structural defects to enhance the compressive flexural strength, okay? Because of the low porosity induced by this reduction in water content, we also have lower permeability. So the concrete is more impervious to water erosions or chemical attacks, okay? So that can keep the structure to live longer, all right? So naturally, it also increases the resistance to weathering. How does that work is, say I have less amount of pores, okay? That means I have less amount of water or moisture goes into the concrete when it's wet. So naturally, we have less of freezing effect, as you all know that from Physics 101. When water freezes, it increases volume, right? The ratio is 11/10, right? 1.1 volume, right? So you have less pore, less intruded water, so less volume inflation, right? Less volume changes. So it has a better weather resistance, okay? And it also increases the bonding between concrete and reinforcement. Okay, what is the bonding? So it means if I stuck a rebar in the concrete, when trying to pull it out, it's going to be very hard if I bond them perfectly. That means whatever stress the concrete is seeing can be perfectly transformed into the reinforcement. So in terms of bonding, we have reduced water ratio, then we reduce the porosity at the interface. So to enhance the materials nearby the reinforcement, hence enhance the bonding between the concrete and reinforcement. Okay, and then next is the reduction in drying shrinkage and cracking. What that happens is when I have less pores, again, after evaporation, I'll have less defects, okay? So when water shrinks, right, it has a less of a shrinkage volume of the cement. So that causes less of volumetric strain, hence reduce the cracking, all right? So overall, what it does is have a less volume change from wetting and drying from the curing process and also for long-term purpose. So reducing water content or reducing water cement ratio is actually very good for our purpose. However, though, I haven't mentioned the disadvantages. The one disadvantage I haven't written here where you'll be tested in the exam is that by having a very low water cement ratio, the concrete is not flowable, okay? The rheology perspective, the concrete is poor, okay? And it takes forever for you to pour the concrete, finish the concrete, and work on it, okay? Now, you gotta figure if you have less water, the concrete can get set in very fast time, right? In very fast speed, right? So normally, without any retardation agent, with a very low water ratio, we're talking about 0.2, 0.3, very low, extremely low, the concrete can get set in 3 hours. And that's not enough for large structures, okay? That's not enough for large structures. And for high-rise buildings where we need to pump concrete over to 20 floors or up, this simply is impossible. Simply is impossible. Why? Because so hard or so pasty the concrete is, it creates a flow layer between the concrete and the tube, prevent that concrete going up, no matter how much pump pressure you added to that process, okay? So not only you need to remember the advantages of reduction of water, but also keep in mind that lower water ratio can cause rheology problem during your working of the concrete itself, okay? So the pros and cons, okay? So apart from this water cement ratio, the very important factor here is we can have admixtures to the concrete. We have air entraining, okay? We have water reducing, we have plasticizer, accelerating, retarding. So the invention of these chemical admixture, main purpose of that is to enhance the workability or strength of the concrete. For example, if my concrete have a flow problem, okay, the concrete simply stuck there, I can add air entrainment, okay? So air entrainment works like tiny lubricants between the aggregates and cement and let the concrete to be more flowable, okay? So it's like if you blow bubbles inside the muddy water, it actually flows faster, okay? And we have water reducing agents. Sometimes what happens, we actually add a lot of water at the beginning to do a fast construction, and where after the concrete is poured, we want the concrete to achieve early age strength, we use water reducing agent to extract the water out, okay? And also we have a plasticizers, okay? In terms of more of polymer content, okay? Essentially, it's by adding polymer to the concrete become more pasty-ish, so it also flows. But the problem of that is with long time exposure of polymer to water, the water dies out pretty fast. So plasticizer is more like a dynamite, right? You're throwing at it, it works like a charm. It gives you an hour or 2 hours of working time, but after an hour or 1 hour or 2 of working time, the concrete starts to set, flash setting immediately, okay? So that's the function of plasticizer. And we have accelerators, okay? That will accelerate the hydration process of the concrete. And then eventually we also have retarding agents that can delay the setting of the concrete to allow more time for you to work on it, okay? So these are the important admixtures we use these days to enhance our workability of the concrete, okay? And we also have other admixtures. If we say these admixtures are immediate, admixtures can have immediate impacts on concrete, and our following admixtures have a long-term effect on the concrete. Most popular ones are corrosion inhibitors, okay? So we have corrosion chemical inhibitors added to the concrete to block the reaction pathway of the corrosion, okay? So we have two types of inhibitor. One is chemically active, the other is physically active. One basically reacts with the chemical agent to slow down the reaction. The other is simply blocking, or by filling the pores, reduce the amount of water can transfer from exterior surface to the reinforcement, okay? Now we also have shrinkage reducers that can reduce shrinkage. ASR inhibitors, alkali silica reactivity inhibitors, that's more chemical inhibitors. We have coloring, and we have all the other things for long-term performance of concrete, okay? So it's very well developed industry. We have so many admixtures to work with, okay? Now, in terms of concrete, if we want to look at the properties of concrete and make sure they're following the standards needed for the design code, the chapter 19 and 20 are the ones we're looking for here. So if you go to your ACI Tech code book, chapter 19 and 20, you can find all the code related information here, okay? All right. So what a concrete looks like in terms of a compressive, right? In terms of compressive loading. Say if I have a cylinder, okay, at the captive bottom, apply pressure axially, squeeze like that, what it looks like, right? And this stress strain curve is what it looks like, right? It will start to go linearly, okay, linearly up, okay, and then go to a peak, reach a peak, then gradually comes down, okay? But it's not brittle, all right? I want you to know that it's not brittle, okay? It's not brittle, all right? And then for the compressive strength testing, we usually use a 6x12, okay? Sorry, let me stop sharing a little bit, switch back to PowerPoint, okay? Some of the animation got lost when I converted PDF, okay? Just give me 1 second. Open up here, chapter 3. Yes. Okay, here, it's the concrete hardening properties. Okay. Okay, we're good. We haven't missing much, but I worry about we have something missing from later. Anyway, okay, so we're good for now. This is the compressive strength, and this is the testing, okay? This is testing. So for testing, we use two types of cylinders, okay? So you can see that there's ASTM C31, there's ASTM C39, two different ASTM standards, okay? But for testing, we usually use 6x12 cylinders. That means a cylinder with a 6-inch diameter, 12-inch height, or 4x8, okay? 4-inch diameter, 8-inch of height. Now the difference between these two, of course, is one is bigger, one is smaller. But you only need 3 cylinders, okay, per set for 6x12, but 5 cylinders per set for 4x8, okay, because of the volume difference, okay? All right, so we talk about the compressive strength, right? We talk about compressive strength. This is what it looks like, okay? Now, there are several critical parameters we need you to understand. The peak strength, or the maximum stress you can get from a compressive strength test, is called F prime C, okay? And later we'll introduce everything that we care about concrete will be related to this parameter here, F prime C, okay? F prime C, okay? This is the critical parameter, you need to know that, all right? As a matter of fact, if I have a different strength, and this is what the curve will look like, okay? You can see that if my strength is low, my curve is pretty flat, meaning I have a reduced elasticity modulus, okay? Elastic modulus, I have a reduced strength, I have an elongated failure strain. But when my strength is going higher, it becomes quite brittle. I have a higher elastic modulus, okay? And a sharper drop in terms of strength, okay? Sharper drop in terms of strength, all right? To analyze this curve, these are some of the information or some of the properties we need, okay? So if I take the tangent line, okay, I will have the tangent modulus of the materials, okay? But instead, we are using the secant. We're using the secant modulus, okay, for the materials properties. And this secant modulus, okay, is actually an equation. Let me put it here. Okay, the secant modulus is actually an equation of the peak stress. Okay, there are two types of formula here. One, we can use the specific density of the concrete, WC to the power 1.5 multiplied by 33 and square root of F prime C. F prime C is the compressive strength we just mentioned. Or we can use 57,000 square root F prime C. Okay, now this equation here, 57,000 square root F prime C is the equation we use most of the time to estimate the elastic modulus or modulus of elasticity for the concrete. That is, if I give you the compressive strength F prime C in terms of PSI, the unit matters, you can plug in here in this equation to get its Young's modulus or modulus of elasticity. Okay, so I think some of you guys, well, actually most of you guys have gone through the mechanics materials class. Okay, so I'm just gonna randomly pick a student to help me out on the definition of modulus elasticity here. Okay, so let me try to go down my list. Adam, Mr. Hart.
Hello?
Hey, are you there?
Yes, I am.
All right, so my question here is modulus of elasticity, right?
Yes,
so
sir.
say modulus elasticity will give us a strain if I know the stress applied to the materials, right? Or vice versa, if I know the strain that the materials is exerting, the material is experiencing, and I have a Young's modulus, I can calculate the stress, right? So in the simple term, that Young's modulus or modulus of elasticity equal to stress divided by strain.
Yes.
Okay, you know that from mechanics materials, right? So
yes.
quick question is, what's the unit for Young's modulus, or for modulus of elasticity?
Shoot, I should know this.
Okay, let me give you a simple choice, right? To have choice one, the unit of modulus elasticity is the same as strain. Okay, that's choice one. Choice two, the unit of modulus of elasticity is the same unit as stress. Is it stress or strain? Which unit?
The stress.
The stress,
Yeah.
right? That's the right answer, right? Because strain does not have unit, right? Strain
Yes.
is ratio unit.
That's right.
Thanks, Adam. So I want you to pay attention here to the class, okay? So the unit for Young's modulus or modulus of elasticity is in terms of stress, okay? So when I use this equation, I have to use the unit for F prime C in terms of PSI, okay? Because square root of PSI give you a unit of square root of PSI. And this 57,000 already have that square root of PSI unit incorporated or embedded, okay? So when you use this, make sure you use the right unit, okay? And once everything's said and done, you have to check the number and make sure that your modulus of the elasticity have a unit of PSI or megapascal or Pascal, okay? So always follow the unit of pressure, okay? All right, good. Okay, so that concludes the compressive strength of the concrete. So in terms of tensile strength of concrete, it's roughly in the ratio between 8% to 15% compressive strength. Okay, now let me say something here for the compressive strength of concrete. We normally divide the concrete by these categories. Any strength below than 4,000 psi, that's weak concrete, and we use for curbside, for some paving, really like a hiking road paving, but not for highway paving, okay? That's low strength concrete. But strengths are below than 6,000 psi, that's called normal strength concrete, okay? So usually 4 to 6, that's a normal strength concrete, okay? Strengths beyond 8 ksi, we call it high strength concrete, okay? We call it high strength concrete, okay? So now, if we say we take a normal strength concrete, say 4,000 psi, 10% of that is, what is 10% of 4,000? Austin Weicker, sorry, you still there?
Yeah, I'm here.
What's the 10% of 4,000?
10% of 4,000?
400.
400.
400, right? Have you done the material testing lab yet?
I did take that last semester, yes.
Okay, so do you know what roughly 400 psi equal to?
It's not a lot.
It's not a lot, right? So give me an example. What's your pressure wash, household pressure wash, normal pressure can get up to?
I actually don't know that.
Okay.
A couple hundred psi, maybe 50, 100.
Yeah, well, actually slightly higher than that. Say, for example, my pressure wash we just bought last week have about 2,000 psi, and that's like household pressure. Okay, so 400 psi is like 1/5 of that, so it's very, very low pressure, isn't it? Right.
Yeah.
So the tire pressure, the tire for your car is about like 30 to 40, right? Tire. So if you have checked your tire pressure, it's about 30 to 40, right? 32-ish, something like that, right? So this is 400. It's about like say what, 10 tires, roughly 10 tires, 15 tires, something like that. Okay. So why I'm saying these numbers, okay? That's what, thanks for the answer. I'm saying numbers is because I want you guys to know that the tensile strength of the concrete is very, very low. Okay, very, very low. Okay, I gave you a comparison. The tensile strength for a really crap steel is about 40 megapascal. Okay, 40 megapascal. Okay, so in terms of PSI or KSI, that's roughly about say 40 megapascal. That's about say actually 5,000 something ish, right? So the tensile strength of concrete is very, very low. So you will never rely on concrete to take any tension. Okay, it's always going to be the steel take care of the tension. Okay, so at this point, I want you to know that. Okay, the concrete is good for compression, and the steel is good for tension. Okay, so never use concrete for tension. Always use reinforcement for tension. Okay, so that's about that. Okay, so since the tensile strength of concrete is so low, of our interest to find out, okay?
We're gonna order a new ping pong net on Amazon.
Oh.
I'm gonna order a new ping pong net on Amazon. You see.
You're not muted. I can hear it. All right, okay, all right, good. So get back to our tensile strength of concrete. I love to order something as well myself, but anyway. So the tensile strength of concrete is very low. So it's about our interest to find out what it is, okay? So there are standard tests for us to test the strength of the concrete, okay? How to do that? This is one typical experiment. This is called 3-point bend, okay? Naturally, you just have a support underneath the concrete beams, okay? In terms of a prism type of specimen, and you crush in the middle, trying to get a crack in the middle, okay? And then we calculate the tensile strength. And this equation here is something, it's very important equation we need you to know to calculate the rupture, okay? So tensile strength of the concrete tested by this method is usually called the modulus of rupture, okay? It's called modulus of rupture, in short MOR, okay? MOR. So that is calculated FR equal to 6 times the moment, bending moment exerted to the specimen divided by the B, which is the width of the specimen, H, which is the height of the specimen to the power of 2, okay? So this is the equation we use to calculate the strength of concrete, tensile, okay? Modulus of rupture, that is, okay? Modulus of rupture. All right, so there are 2 types of tests. We have the 4-point load and we have the 3-point load, okay? So this 3-point load, okay, now they call it center point loading, that's fine. But the lower scheme here, so let me say, do this, so you can use that. This scheme right here, okay, is the most often used. It's the most often used, okay? This is the most often used test, okay? All right. Okay, now for the tensile strength, there's another way to get it faster is using the same cylinder, okay? Same cylinder. What happens is we apply a line of pressure on top of the cylinder by supporting 2 ends of it, okay? So through this experiment, we also get the strength, but the stress distribution is not uniform. The stress distribution is not uniform. As you can see there, when we apply a pressure on the top and bottom here, there will be concentrated compression. There will be concentrated compression, okay? And then afterwards, we'll generate a tensile stress in the middle of it, okay? So when the tensile stress in the middle reaches this peak strength and it busts it, okay? Then it busts it. So the equation to calculate this type of test is called split cylinder test, right? It's just splitting a cylinder. Is that FCT, okay? Know the subscript FCT equal to 2 times applied pressure force, okay? Applied force P divided by pi LD, okay? L is the length of the cylinder, D is the diameter of the cylinder, okay? So that is the equation used for tensile strength of concrete tested from split cylinder test, okay? Split cylinder test, okay? So there are a lot of standards, okay? For the sake of time, I have this, you can watch on the YouTube video how they test it, okay? So we're just gonna skip real quick, okay? So there are relationships between compressive and tensile strengths, okay? So we know that they grow proportionally. If the compressive strength is high, then the tensile strength normally is high, okay? And the ratio between the tensile and compressive strength decreases, okay, as the compression strength increases. So there's a limit, all right? If you increase the compressive strength indefinitely, your tensile strength does not increase correspondingly, okay? Does not increase correspondingly. So we say that tensile strength is roughly in the proportion with the square root of compressive strength F prime C here, okay? Roughly, okay? All right, so this is an important fact you need to know for the exam. Okay? All right. So for the strength of the concrete, normally we test the compressive strength of concrete. And sometimes we just don't have means and ways to test the tensile strength of concrete because it requires facilities, okay? Required facilities. So what we do usually is we use the compressive strength F prime C to estimate the tensile strength of the concrete. So there are 2 tensile strengths we just mentioned, right? One is called the split cylinder, which is FCT, okay? And the other is directly from the beam bending, we call it FR, okay? So these are 2 types of tensile strengths, okay? And actually the relationship, okay, estimated relation between them is that the split cylinder have a 6.4 times square root F prime C, and the modulus of rupture equal to 8.3 of square root F prime C, okay? But for deflection calculations in our code, it's 7.5 lambda square root F prime C, okay, for modulus of rupture. Now, for your homework, I want you to use this equation universally, okay? 7.5 lambda square root F prime C. Now, lambda is a type of concrete coefficient, okay? Normally equal to 1 for normal weight concrete, okay? Let me type this out, normal weight concrete, okay? Normal weight, okay? And lambda will equal to what? Lambda will equal to a 0.75, okay? Okay, let me write down here. That equal to a 0.75 for lightweight, okay? For lightweight concrete, okay? So be careful when you read from the problem, okay? Sometimes it's lightweight, sometimes it is normal weight, okay? So we have a different factor here, okay? So the reason behind it is that when we have a lightweight concrete, there are aggregates are porous sometimes. So those are weaker aggregates and reduce lower stress, okay? Lower stress, all right. So there are 3 types of changes in term volume for concrete as well. We have a shrinkage, okay? We have a creep, we have a thermal expansion, okay? So I want you to remember that the concrete will shrink with time. And if you apply a pressure on the concrete for a very long time, it will also have a permanent deformation that is called creep, okay? And if you heat it up or during the curing process, the heat inside the concrete itself can expand, right? Can expand the concrete, okay? All right, so talk about the shrinkage, right? What type of shrinkage we have? First, we have the shortening of the concrete due to hardening, drying under constant temperature, that is, okay? So moisture means water just come out from concrete through diffusion, okay? And we have the outside surface that shrinks faster than the inside. So normally you see a lot of cracking, when the shrinkage occurs, okay? When the shrinkage occurs, okay? So we have a shrinkage versus time. So most of the shrinkage you can see that occurs in early stage during the concrete curing process, okay? During the concrete curing process. When the concrete get hardened, you don't see a whole lot of shrinkage anymore, okay? All right, so for the volume change, the other more important factor is creep, okay? Important factor is creep, okay? So for now, I want you to know that there's a certain threshold, okay? You apply a strain, okay? At the first, doesn't change, right? First, nothing changes. Until you reach a certain threshold, you immediately see a creep, okay? And this strain is elastrain. If you keep loading it, keep putting the pressure on it, it gradually increases more, and more. All of a sudden, at this point, say you unload it, you remove the loading. First, it will go through an elastic recovery, means this part of the strain will recover, okay? And then it will go over a creep recovery, means some of the creep strain will recover, but you still end up with a permanent deformation, okay? Permanent deformation, which is quite a big portion in terms of creep, okay? So one message I want you to remember about creep is that creep will cause permanent deformation to your concrete structure. So creep is bad, okay? Creep is bad, all right? So the creep strain can lead to increasing a deflection in time, means your bridge can sag, your building can collapse, well not really collapse, but can shrink or can tilt like the Pisa Tower, although Pisa Tower does not tilt from the same reason. And then also can cause redistribution stresses. Basically, some of the member might give up and he has to take more load, okay? And also decrease the pre-stressing forces. And you learn from the lectures in senior classes where you use pre-stressing concrete. Basically, you pre-stress a tendon reinforcement to let the structure become more rigid, can take more load. But if your concrete creeps and you just reduce that force, right? So that does not have the effect you wanted, okay? So that's a problem caused by creep, okay? And the thermal expansion basically come from the composition of the concrete, moisture of the concrete, and age of the concrete, okay? So you just need to know this. We most likely will not test this, okay? So a quick number you need to remember are the coefficient of thermal expansions, okay? It's about 3 to 5, it's about 3 to 7. And unit here is very important, okay? 10 to the power minus 6. Strain means no unit per degree, okay? Per degree. So I want you to remember this unit, okay? Unit is right here, okay? So these are the roughly level of the coefficient of thermal expansion. As you can see that 5.5, this number here is the standard value we use for concrete, okay? Standard value we use for concrete, okay? So not so much to worry about for concrete, okay? So far, let's do a quick overview or quick cap. All you need to do when you get the concrete, okay? First, you do the compression test to get the F prime C, okay? You do the compression test, get F prime C. If you have facility, you do the tensile test to get FR, modulus of rupture, at FCT, okay? Split, concrete cylinder split tensile strength, okay? If you don't have that, if you don't have these ways to test the concrete, okay? You use this equation 7.5 lambda square root F prime C to estimate the tensile strength from the compressive strength. But regardless, okay, regardless, you always have to do the cylinder crushing test, okay? You always have to do the cylinder crushing test, okay? This is the must, okay? This is the must. All right, so that's all about concrete, okay? So let's talk about steel. Now, there are so many types of reinforcement for the reinforced concrete structures, okay? There are deformed bars, welded wires, and pre-stressing steels, okay? So for the deformed bars, they look like something like this, right? When I have a bar and I have ribs on the surface. So it's about the time to wake you up again. So I'm thinking about the question, why do we need to have ribs? Why do we need to have ribs for the bars? Okay, so I'm gonna call our next victim. Who's on here? I'm gonna pick Dalton.
Yep.
You still there?
Yes, I am.
All right, great. So the question is, why do we have to have ribs in a rebar? Why?
My guess is so that it can adhere to the concrete better, so that way there's no slipping with inside the concrete once it's placed.
Exactly, right? The slipping, right? So let me ask you this question then. Do you think we can put any rib on the surface of the rebar, or it has to be a specific shape?
I am not sure. My guess is it would depend on what we're using it for, what type of reinforcement it is.
Okay, that's a good question. So I'll let you go on this. So yes or no? Yes, it does depend on it, but no, we don't care that much. Reason is because cost, right? So unless we have different molding, we can actually fabricate different rib geometries to achieve the ultimate purpose, like you were saying, Dalton. Unfortunately, the industry is a pretty standard industry, okay? So what happened is we, back then, and during the Second World War, actually right afterwards, United States tested thousands of bars from the manufacturer point of view, okay? And they find out a specific geometry and ratio that give you the highest bonding strength between the bar and concrete and call it good, okay? So right now, as a market, you can see that most of the ribs, okay, like the rib right here, look like this, okay, especially this threaded, okay? We have some of the helical ones, but more nowadays, more like this, okay? The spacing between the ribs over the rib height is usually normally between 7 and 10, okay? Normally between 7 and 10, and that's why we have a standard shape for the ribs, okay? All right, so that's about the bars, right? We know that there are deformed bars or welded wires. We don't use welded wires for the main columns or beams as a reinforcement. We usually use welded wire for slabs, okay, or some rail structures that does not need structural reinforcement, okay? And then for the pre-stressing steels, we usually use strands, twisted strands, okay? Each individual wires, twist them together to sustain larger tensile strengths, okay? All right, so there are a lot of standards for the rebars. I don't have to elaborate, you can find them. But I want to talk about the reinforcement details or these markings on the reinforcement, okay? These markings on the reinforcement. So let's take a quick look. So on the rebar, you see these numbers, okay? On the rebar, you see these numbers, okay? So the first letter is a symbol for the producing mill, okay? From the producing mill, where it comes from, okay? Next number is bar size, okay? The size of the bar, okay? And then the last number here, S here, means is what type of steel, okay? What type of steel. So if it marked with S or W, it's meeting most of the A615 and A706 standard, okay? 0706 standard. Now, you can see that some of the bars have a great mark here, 60, okay? Now, this great mark here, 60, represents the strength of the rebar, okay? So this right here, H11S60, these are the critical parameters, okay? Critical parameter for a rebar. So if you're a civil engineer, you go on a job site, you pick a rebar, you read these letters, you can tell the construction workers what type of bar they are, okay? You should be able to, okay? Or they'll laugh at you. I'm just joking, but anyway. So for the bar, deformed bars, okay? These on the first left-hand side, this is the column for the number of size, 3, 4, 5, 6, you know, you name it, etc., etc. And these are the area, cross-section area of the bars, and these are weight, and these are diameters, okay? So I want you to take a quick look here, okay? 0.375, that is equal to 3/8 inch, isn't it? That's 3/8, right? And 0.5 naturally is 4/8 inch, isn't it? So let me do this. Let me try to hide these two columns here. Okay, so let me just delete these two columns, okay? Only left with this, all right? Okay, so I keep typing, and this is equal to actually 5/8 inches, right? So I keep typing, this is 6/8 inches, all right? So a quick question here, quick question here. Bryce?
Yep, yes.
Good to have you here. So can you make a guess of what number should I type in here?
7.
7/8, right?
Yeah.
So how do you tell?
It just goes up by 1/8.
That's right. So essentially, how the bars are numbered is 3, 4, 5, 8. Okay. So when we say number 3 bar, it's 3/8. Number 4 bar is a 1/2 inch. Number 5, etc., etc., etc. Okay, so this is just some of the rules that we use to remember the bar size. Okay, some rules we remember bar size. Matter of fact, right? Matter of fact, if I recover it for this simple trick here, you can actually use that to calculate the area. Okay, calculate area. There might be a slight off just because some of the rib were not considered. Okay, some of the rib were not considered, but this is roughly equal to the conversion from the diameter. Okay. All right, so let's talk about the strengths. The black curve here is the tensile strength result of the single bar. Basically, I put a bar, a hook on one end, and drag the other end and just tensilely stretch it, right? And I have a curve and divided by the nominal area. Keep in mind, nominal area, the area start with. I get this stress strain curve like this, okay? And you can see that I follow a nice linearly curve like this. I have a bump, okay? And then gradually come up again and goes down again, okay? Now, really keep in mind here, okay? This curve is for hot road steel, okay? For hot road steel, okay? Cold road steel does not give you performance like this, okay? You probably will know that from the steel structure design course later, but this is for hot road steel, okay? For hot road steel. So the distinct feature of the hot road steel is I can use this dashed line serve as a back end envelope of this curve, okay? Back end envelope this curve. Basically, I can say your stress strain relation for the steel bar is linear line and flat. Linear line and flat. And I'm going to take this peak strength here, Fy of this flat portion as the yield strength, very important, okay? Yield strength of the reinforcement, okay? Fy, this is called the yield, okay? Yield, Y-I-E-L, the yield strength of the rebar, okay? Yield strength of the rebar. And this is our design strength, okay? So that means the grading we're talking about here, 60, okay? The grading we just talked about here, 60, is actually the yield strength of the bar, yield strength of the bar, okay? So how so? So if the grade is 40, that means I have a minimum yield strength of 40 KSI, okay? KSI. The ultimate strength is 70 KSI, but I tell you what, I'm gonna save you the trouble. Just go ahead and delete this, okay? Delete this. All you need to know for the reinforced concrete structure course is this, okay? Is the yield strength, okay? Yield strength, okay? So Fy is everything we need to know, okay? So 40, grade 40 means 40, grade 50, 50 KSI, grade 60, 60 KSI, 75, 70 KSI. You usually do not see any number beyond 75, okay? That's as high as you can go, okay? That's high as you can go. Okay, so I'm gonna make a quick test here. Okay, I'm gonna say I have a grade 60 rebar, and I have a grade 40 rebar. And naturally, 60 is higher than 40. Okay, so for the sake of construction, should I use all high strength rebar or should I use different strengths of rebar? I'm gonna call Aziz, Alamari.
Yes.
So should I use universal strengths for the rebar for all my buildings, or I can use different strengths for different locations?
The universal one.
Why do I use universal?
Following the book.
Well, yes or no, okay? Following the book, following the industry standard, we want to use universal to save cost. You're absolutely right. But
yes.
Actually, for the design purpose, we use different size, okay? We use different grade. Okay, but that's close, okay? Thanks. So normally for the stirrups, for the hoops, okay, for some shear resistance, for the tiny size stirrups, where we cannot have large diameters, we can only use number 3, okay? Number 3 or number 4 bars. That means if we use number 3 and number 4 bars right here, okay, we will only pick about 40, okay? We'll normally pick the 40, okay? Grade 40, they're usually grade 40, okay? If we use number 6, okay, number 6 or number 8 above, okay, if we use this as the main reinforcement of beam and columns, okay, usually we use grade 60, okay, grade 60. Sometimes we use grade 75, okay. So you can take a look at this. The yellow highlighted 40 usually for stirrups, for shear, for hoops, and 60 and 75 are for main columns and buildings, main structures, okay? So these are some subtle differences, okay? All right, at this point, we are actually done with chapter 3. So let me quickly recall, okay? So for the concrete, this is some of the questions I might ask, okay? Some of the questions I might ask. What kind of experiment or what kind of a test I'm going to perform to get a compressive strength, okay? And that is the concrete cylinder test, right? Compressive strength of concrete cylinders, right? And I forgot to mention, I need to mention here. So usually we test concrete cylinder at different time here, days, okay? We have the 3 days, 7 days, okay? These are called early age strengths. Early age strengths. Basically, we need to know whether the concrete is good or not, okay? And in the construction industry, if you cannot achieve the specified 7-day strength, you need to knock your building down, okay? You need to knock your building down, okay? So very critical. And then we use the 28 days results as the compressive strength of the concrete, okay? 28 days of strength as a compressive strength of concrete, okay? So be very careful here, okay? Now, for the steel, the most important thing is the yield strength, okay? Is the yield strength. So we need to know we are designing based on this yield strength, okay? Fy here, okay? Of course, the size and marking, I'm pretty sure you got a handle of it. They're not difficult at all, okay? So for now, we're just done with the concrete and the steel part of it, okay? Any questions? Any questions for the steel and concrete part, guys? Anything you can think of it? Anything? All right. So I know you might be thinking about it, or it's the Thursday afternoon. Everybody's tired and ready to go home. But let's stay on a little bit. I want to walk you through some of the homework problems. Okay, some of the homework problems. First, let me stop